You saw in the last TV program how a wave profile like this could be used to represent the amplitude transmittance of a cosinusoidal diffraction grating with period d. But you should also remember from that program that we could represent the same information by plotting out the frequency components. In this particular case, there'll be a frequency component at 1 upon d, another component at minus 1 upon d, and in order to keep the transmission always positive, there must be a zero frequency component. We then saw how it was possible to use this model in order to understand why, when infinite illumination came up to a cosinusoidal grating, it suffered diffraction, so that the light came out at an angle. Furthermore, we saw that we could add cosine gratings together to make more complicated gratings, such as this one, for instance. Here, this square wave grating was built up of lots of cosinusoidal patterns, and of course, these cosinusoidal patterns had to be of different frequencies. So when we go to the other representation of this wave profile, we find that we've got a lot more harmonics. In fact, you can see there are harmonics both positive and negative, plus, of course, a component at zero frequency, again, to keep the transmission wholly positive. Now, what we want to do in this program is we want to expand this. We want to enlarge our repertoire of this dual representation.
Well, the trouble so far is that we've only been considering gratings that we could consider to be infinite. And the trouble with that is that in the real world, infinite gratings simply don't exist. And the reason that we've been able to get away with it up to now is that across the width of the laser beam, there have been very many grating periods. To all intents and purposes, the grating has been acting as if it were infinite. For example, consider this one. This is the diffraction pattern of a square wave grating, which can be considered to be infinite. Well, let's get into that and have a closer look to see how it might change as we consider different cases. There we are. We'll just concentrate on those 3 spots there. Consider this. Quite a lot of structure between the spots now. And what about this one? Quite different. You see, what we're doing is making the grating, in a manner of speaking, less and less infinite. And we've ended up with the limiting case of just having a single slit. And the intermediate case that we pass through, what do you think that is? Well, it's simply the case of a restricted grating. How is it that we can account for the diffraction patterns of gratings that, not even approximately, can we consider to be infinite?
But that's not an easy question to answer. The problem is that we need to know what the frequency spectrum is. You saw in the unit that you could go on adding up cosine curves to see what you finished up with. That's a tedious business. We could have tried doing it electronically on a synthesizer. What we've chosen to do is we've chosen to do it with a computer. I've programmed the computer with some functions in X space, waveforms. In fact, the display up here is already showing the square wave grating. And as we step the computer on, what it will do is calculate the frequency spectrum. It'll display that down here. Let me do that now. OK, we know exactly what that display is. We've already seen it over on the board. What I now want to do is I want to open up the waveform so that we've got a bigger gap between the pulses. I'm not going to change the width of the pulses, leave the pulses the same width, but spread them out. And I want to see what happens to the waveform. Let me try doing that. Let's try opening out a bit further. Now the harmonics have actually closed in. As the pulses moved out in space, the harmonics moved in Q space. But notice that the amplitudes of the harmonics seem to be following a fairly fixed profile. Let's go one step further. Now there are only 3 pulses in X space at the top, and the harmonics are pretty close together now in Q space. One more step. The frequency components are now so close together that it becomes rather meaningless to talk about the amplitude of individual components. Instead, we talk about the frequency spectrum, the harmonic envelope. Sometimes we simply say that this is the Fourier transform of the square pulse, or we sometimes call it the Fourier mate, or more commonly, we simply refer to these as Fourier pair, as a Fourier pair. Instead of plotting out all the harmonics, we simply plot the envelope. This particular function is called a sinc function.
Well, this is the single-slit diffraction pattern that we met earlier. It's one of our problem patterns, one of the ones that we have to account for. Well, now Keith has developed a theory for it, so let's see how the theory measures up to the pattern. There we are. At the top, we can consider that single pulse to represent the transmittance of our single slit. And beneath it, we have the sinc function, which we can think of as the diffraction pattern produced on a distant screen by the single slit. And I think you can see that there's a qualitative agreement between the actual pattern we obtained at the bottom and the sinc function there in the middle. But of course, there's one qualification we have to make here, and it's this, that the sinc function represents the field on a distant screen, whereas the diffraction pattern is the intensity. Well, of course, all we have to do is to square the sinc function, and I think you can do that in your minds well enough, and you can still see that the essential correspondent remains between the intensity pattern that we actually observed and the pattern that we've derived by theory. Well, let's put that result on the board. We started off with this function here, which I think for pretty obvious reasons we call the top hat function, and its Fourier transform we've got alongside it, and there it is. We call that the sinc function, as you already heard. These two, taken together, form a pair of mates, Fourier mates. We've got another pair of mates to add to our list.
But before we get carried away with Barry's explanation, let's remember he only had one slit there, a particular slit, a fixed width, a fixed profile. We could have changed that, of course. We could have narrowed down the slit width. Or suppose we'd had a photographic negative. Suppose the transmission didn't go from 100% to 0% transmission, but had some intermediate values. Suppose it had a funny profile. We've got to explain what would happen under those situations. Let's take them one by one. Let's look at what happens when we narrow down the pulse. So let's go back to the computer. I've got up here the single slit again in X space, and here is the frequency representation. Let me now narrow this pulse at the top and look at the frequency spectrum. Well, there are a couple of things happened here. First of all, the sinc function has expanded outwards. That might have been what you expected. As the pulse narrowed down, the frequency spectrum, Q-space spectrum, moved outwards. But it's also gone down in height. Now, think of the physics. Think what's happening in terms of physics. Suppose that really were a single slit and light was going through it. Well, of course, as the slit gets narrower, less light goes through. There's less energy there. Now, if we're thinking of that energy being distributed out along the frequency spectrum, then obviously the amplitude of the frequency components must also go down. There's less energy there. As we keep on narrowing the pulse right down, the spectrum is going to get smaller and smaller and smaller, till eventually we just won't be able to see anything. Now, this is a nuisance. So what I've done is I've programmed the computer to normalize this, to bring it back to a full height. Here, the spectrum is just the same, except now the height is back to the height we had before. We'll do this all the way through this sequence, but remember, in practice, it ought to be going down. Let's narrow the pulse down a bit now. And here, the frequency spectrum has moved even further out. It crosses the axis just before it goes off screen. An even narrower pulse. And now the frequency spectrum doesn't cross the axis at all. And here, in the limit, when this pulse has got very narrow, the frequency spectrum is a continuum. Well, that's the first problem. But what about the other question I raised, the question of changing the wave profile? Again, what I'm going to do is look at the computer results. I'm going to take that single spike, and I'm going to expand it up. But I'm going to expand it up not as a square pulse, but as a funny shape. The particular shape I programmed in is a Gaussian. And its frequency spectrum? Well, you can't actually see very much from this. It's perhaps dipping a little bit at the outside, but it's not terribly clear. Let me expand the Gaussian a bit more. And the frequency spectrum here, well, it's coming down now. This is what we'd expect, the same reciprocity. As X space at the top moves outwards, so Q space moves downwards. Let's keep going. And again. Well, this is obviously not the same function at all. This is not a sync function. It doesn't cross the axis. It doesn't oscillate. In fact, this is a mathematical peculiarity because, in fact, this function is its own Fourier transform. A Gaussian Fourier transforms as a Gaussian. Let's go to the extreme in X space where we have a continuum and the frequency spectrum is again a spike. So a continuum transforms to a spike. Let's try a different function. We start again with the spike, and its Fourier transform in Q space is the continuum. Let's expand that spike out as a triangle in X space now. Well, again, at this stage, you can't say very much about the frequency spectrum. You certainly can't tell what shape it is. Let's go a bit wider with the triangle in X space. Well, there's certainly something happening here. It's actually oscillating. In fact, it turns out that this function is sinc squared. The Fourier transform of a triangle is sinc squared. And in the extreme, again, the continuum transforms as a spike. One final profile. Let's start with a spike again, and now expand out as an exponential. The exponential decays either side of the origin. And its Fourier transform is a Lorentzian. This is a function which looks very similar to the Gaussian, the bell-shaped Gaussian. It is marginally different out in the wings. As we narrow down the exponential in the top trace, the Lorentzian in the bottom trace expands out. And in the limit, the continuum transforms as the spike.
Well, let's summarize some of those results. What we've done is to add a certain number of mates to our board. We've seen that the Fourier transform of the triangle is the square of the sinc function, that the Fourier transform of the Gaussian, that's the special case, because the Fourier transform is itself a Gaussian, and that a two-sided exponential Fourier transforms into something that we've called a Lorentzian. Now, the relationship, the way that we did it, the way that we established these relationships was from going from here and ending up over there. But we could equally as well have gone the other way. We could have said, well, this is our function in frequency space, and asked the question, what is it in X space, in ordinary space? And indeed, if we started off with that, we would have ended up with this. We could have worked the other way. Equally well, we could change around these symbols. This, for example, could be the transmittance of a rather funny object, if you like, in real space, in which case this would have been its frequency spectrum, its spatial frequency spectrum. Now, not only do the mates belong together, they're tightly coupled, if you like, the one goes with the other, but also so does their widths. As we narrow down one of them, the one in the other space must increase. And in the limit, we saw that regardless of the precise shape of the function, as the one narrows right down, the other one opens right up. That's another property that we can use to go from one space to the other. Now, the reason that we chose these three particular pairs is because they're pairs which occur quite often in practice. But the sort of things that we've been talking about, in fact, can be applied to very many other pairs, in fact, to any pair. For any one in one space, there is a definite pair in the other space, and for a width in the one space, there is a very definite width in the other space. And that's just two of the very many properties that, in a sense, couple the two spaces together.
Well, we've cracked the problem of the single slit. We've even gone further than that. We've solved the problem of really complex profile single slits. But what about that other problem, the problem of the restricted diffraction grating? Perhaps the best way into this is to look at how we made that diffraction grating. I've got a replica of it here, and all it was an infinite grating. Well, not infinite, it was actually about 2 centimetres across, but certainly much bigger than the diameter of the laser beam. And I stuck black sticky tape across it, 2 pieces of black sticky tape, leaving a gap between them of the order of 1/5 of a millimetre. Now, 1/5 of a millimetre is much less than the diameter of the laser beam. Of course, in this situation, this forms a restricted grating, and this is what we got. Let me summarise that. A restricted grating with only a few pulses in it can be thought of as being made up of a single slit, which is multiplied by an infinite grating. I overlaid the single slit over the infinite grating. Now, is this a useful breakdown? Well, I think it is, because we know what the Fourier transform of an infinite grating is. We've seen this many times in the program already. We also know what the Fourier transform of a single slit is. It's the sinc function. So, if we can actually build up the limited diffraction grating in X space by multiplying together 2 other functions, how do we find the Fourier transform of this limited grating? Do we just multiply together these 2 component Fourier transforms? Well, this is not obvious. Rather than make a step like this without any justification, I'd rather look at what the computer says the true answer is. Let's punch it up on the board. Here to begin with is the infinite square wave with its frequency spectrum. Now let me actually cut off the ends of this infinite square wave. And the frequency spectrum now? Okay. What we've got in this case is a layout which is very similar to the layout of the single spikes, but we don't have spikes there anymore. We've got some funny wiggles. Now, if you look carefully at those wiggles, I think you can see that they are the sinc function, turned upside down where they should be turned upside down. What we've done is not multiply those 2 Fourier transforms together. We've done a sort of dealing act. We've dealt the sinc function, which is the Fourier transform of the top hat, to all the positions indicated by the Fourier transform of the infinite grating. We call this operation convolution. Perhaps we ought to have a look at that diffraction pattern again.
Well, here it is. That's the diffraction pattern of our restricted grating. Does it bear any resemblance to what Keith has produced for us on the computer? Well, yes, indeed it does. You can see that around each of the main maxima there are subsidiary maxima. In fact, those arise from the sinc function, which is being dealt to each of the main maxima. Now, in fact, that was a relatively straightforward case. And it was straightforward because one of the functions that we were talking about, namely the infinite square wave grating, was in fact infinite. And that's relevant because it generated a Fourier spectrum which consisted of a series of well-separated spikes. And spikes, well-separated spikes, are easy to deal to. But what happens in a case when neither of the functions is infinite, that is, when neither of the Fourier spectra is spiky? Well, here is one such case. Let's store that. There are many ways of representing this as the product of 2 functions. One way is to start with a top hat and multiply it by a 2-sided exponential. The top hat chops the wings off the 2-sided exponential. To obtain the Fourier mate, we have to take the mate of the top hat and the mate of the 2-sided exponential, which is a Lorentzian, and convolute them. But how? Well, one way is to take the Lorentzian and divide it up into strips. The sinc function is then dealt to each strip. All the sincs are then added together to give the resultant, which is the Fourier mate of our starting function. The exact form of the resultant is given in the broadcast notes. Well, we could in fact have got the same result by a rather different route. We could have split the sinc function up into strips and dealt the Lorentzian to each strip, and we would have come up with the same resultant. Well, what we've established is rather an important theorem. It's called the convolution theorem. What it says is that if we have a function a, which is equal to x times y, then the Fourier transform of a is equal to the Fourier transform of x convoluted with the Fourier transform of y. That funny symbol there, that cross with the circle around it, means convoluted with. And in fact, the convolution theorem works the other way around. If it's convenient to regard A as x convoluted with y, then the Fourier transform of A is equal to the Fourier transform of x times the Fourier transform of y. You see, all we have to do to get the inverse theorem is to exchange the multiply sign with the convoluted with sign. The importance of the convolution theorem is that it enables us to generate mates, Fourier mates, from mates that we already know.
Well, before we leave this subject of Fourier transform pairs, I want to introduce you to a rather surprising thing. Because we've introduced this theory for diffraction gratings, for spatial frequency components. But this is a fairly recent innovation. Historically, it started with a representation of amplitudes in time transforming to temporal frequencies. In fact, we can summarize it by saying that X space should transform to spatial frequencies, whereas time would transform to temporal frequencies. Everything we do in time, everything we do in space, are equivalent. Whatever we do in space, we can duplicate in time. I want to try and prove that to you by doing a demonstration. An oscillator, which is equivalent to the infinite sine wave grating. But I'm going to switch this oscillator, this pure tone, on and off with a box. Now that's equivalent to putting like sticky tape over my grating and restricting its width. What I'm then going to do is I'm going to narrow down the width. Now, I want to hear what happens to the frequencies. I can't actually show you on a spectrum analyzer. I'm going to let you tell me what happens simply by listening to the note. Let me go through the sequence. Let me just repeat that last one with a different time scale on the oscilloscope so we can see what's happening. Only a couple of cycles coming through. That's rather like having two slits in our diffraction grating. What was happening? Well, you were unable to tell the precise tone that was coming through at the end. It had degenerated into a click. Why? Because as we narrowed it down, in frequency space, the frequencies were spreading out into a sinc function pattern. As they spread out, there were more frequencies there, all adding up to produce this metallic click. So we seem to have come rather a long way from our rather idealized infinite gratings. Not only have we been able to explain what happens when the gratings aren't infinite, but are very finite, we've also been able to explain what happens when we get right down to a single aperture. Fairly complicated apertures at that. Even more, we've seen that this formalism which we derived, this Fourier transform formalism, can also be applied in the time domain. In fact, Fourier analysis is a very powerful technique. We'll be using it over and over again in this course.